Guys, I want to start. Thanks. This talk is titled ET Count Phone Home, Security Issues with Voice over IP. Voice over IP is a very nice technology that some people are using in different architectures, and I'm going to talk about that as well. There are huge amount of security issues with voice over IP that sometimes companies that sell the technology or enthusiasts don't like to deal with. I'm going to show you some of the issues. I'm going to talk about some of the issues, and I'm going to have some slides that will show you exactly where you're vulnerable, why you are vulnerable, and I'll show you some other hints that I've been working on as well that relates to bigger and more and even more harsher problems with voice over IP. I should say this, I didn't say it in the start. My name is Ofir Arkin. I work as a managing security consultant or architect for AtStake. So, we're going to talk about voice over IP. We're going to talk about the generic threat model with voice over IP. We're going to examine the session initiation protocol. We'll go through the threat model for that protocol, and we will show and explain RTP, the real-time transport protocol, which is being used to carry voice samples. So I'm going to start with some overview about IP telephony, voice over IP, and voice over net. IP telephony can be defined easily as the use of IP networks to transmit both voice and data packets. Voice over net, or in its other name, internet telephony, is used to describe the usage of the internet to transmit those voice and data packets. When we usually refer to voice over IP, we usually refer to the usage of some kind of a managed IP network that we control that is being used to transmit those voice and data packets. Usually those networks are being associated with either a carrier class network or a corporate LAN where we can control the network. If we look at the history of the of IP telephony, then voice over network was the first to be found. If you remember a company called Vocaltex and their internet phone back in, I guess, 1996 or even 1995, voice over network or internet telephony was the predecessor of voice over IP and actually contributed to the development of voice over IP and IP telephony as a whole. The main development of IP telephony is being done these days at the Internet Engineering Task Force. Many of those protocols are still in the development stage under the IETF. The problem here is that new protocols or new versions of the protocols are being drafted and even being agreed as a standard track. And when you look at security, this is still a bad thing. If you want to have products that will be using these protocols, it's kind of hard to understand from the manufacturer side what exact draft or what exact protocol it needs to relate to. There are a number of architecture where we can deploy IP telephony. First of all, and is the internet telephony itself. Internet telephony service providers, which are those service providers like you can use them with MSN Messenger if you want to place calls over the internet, corporate LANs, and of course converged network architecture, which is usually associated with a carrier class network. With any IP telephony architecture, we can have several protocols that combine that architecture. First of all, signaling protocols, media transport protocols, and some supporting protocols. The signaling protocols perform the following services. First of all, they locate the user. This is basically the ability to find the user which we want to communicate with. The second thing that they are dealing with, or the second service they are providing, is session establishment. This is basically our ability to accept a call, reject a call, or redirect a call to another location or service. There is also a session setup negotiation where parameters such as audio encoding are being negotiated. We can modify a session as well. This is the ability to change the audio encoding, for example, and remove a participant and such and such. And of course, we need the ability to tear down a session. On the other hand, the media transport protocols are actually in charge of carrying the voice samples themselves. The major protocol that is being used today is the real-time transport protocol, or RTP. These transport protocols are usually using some kind of a codec that digitizes the voice, compresses it into small samples, and it will be encapsulated inside an IP transport protocol, which is usually UDP, and transported using the IP network. If we're looking at the supporting protocols, some of the supporting protocols that are out there are mainly quality of service protocols, such as diffserv, inserv, RSVP, and the rest. DNS, with or without special extensions, routing protocols, and other protocols. As I said before, ITF is the main leader of this development. Its own voice over IP architecture is based on a number of protocols, and of course, only a small part of them produce actually a complete solution. This gives the ITF's voice over IP architecture a very good flexibility and a very good way of developing these protocols. Now, for a small definition here is actually what is needed with the telephony architecture, which connects with the regular PSTN. We need to have some elements that will translate the signaling and voice samples between that PSTN, the regular telephony network that we know today, and the voice over IP network, and vice versa. Therefore, we should have some kind of gateways in our network in order to do so. The first gateway that we need to have is the media gateway. It's the element in which converts audio signal carried on the telephone circuits into data packets, and of course vice versa. This gives us the ability to actually get the voice samples. The media gateway controller, which is controlling the media gateway, and a signaling gateway, which controls the signaling used on the IP network with the signaling used on the PSTN, which is the signaling system 7 network. Looking at all of those signaling protocols, we can also divide them into certain groups. Protocols that are used between media gateway and the media gateway controllers for control purposes. Protocols that use between the media gateway and the signaling gateway. Protocols that use between the media gateway controllers to exchange some information between them and to be synchronized. And protocols used within the IP network itself. This is the voice over IP architecture that is being pushed by the IETF. You can see that this is our IP network, which I'm trying to put the borders with the mouse cursor. We can see that our IP network is being communicating with the media gateway controller, and through the media gateway controller, we are communicating to the signaling system 7 signaling network with the PSTN, and through the media gateway, we're directly connected to the PSTN in order to translate the voice sample from the IP network to the PSTN and vice versa. If we're looking only at the IP network and we wish to look at the session initiation protocol and what are some of the elements that one needs to have in its network, you can see that we have here only IP-based elements. We have a SIP user agent, which is the endpoint, which is able to communicate directly with another endpoint, or to communicate with a SIP proxy that I'll explain in a couple of minutes what is its role. If we're looking at security, the following sentence summarizes very well the problems with voice over IP security. Someone said that it is no longer necessary to have a separate network for voice, and I think that it pretty much says it all. First of all, the uses of IP. When we're using IP, we inherit all the problems that are associated with the IP protocol regarding security. The second issue, or even a more complex issue, because we need to understand what is the nature of speech. We need to understand that we have to have voice quality, and voice quality is a must. If we don't have a voice quality with our voice over IP network, nobody will use the network. They'll all go back to the old PSTN equipment, and nobody will earn anything from it. So we must have voice quality. Now, in order to maintain voice quality, we need to make sure that some parameters are being met, and we're going to take a look at that in a moment. And of course, if we examine the poor quality of the voice over IP protocols themselves, and from the different architecture which the IP telephony is being deployed, this is another venue for trouble. Usually those protocols are being used or are being developed by people who has some kind of a business notion to that particular area, and sometimes the decision that the ITF makes and the groups that the ITF impose makes are totally non-relevant to the security world, but relevant to the business world. This is kind of a funny slide. If you can look, this is a slide or a screenshot from Ocean's 11. You can see here, this is a nice Cisco IP phone hanging behind Mr. Zerga just before they hit the Bellagio safe and the movie. It kind of reminds me the Coca-Cola versus Pepsi wars of the 80s, where you've seen movies that you see a can of Pepsi or a can of Coke on a guy's desk by mistake or whatever. If you watch the show 24, you can see other voice over IP phones deployed wherever you like, and people using voice over IP phones and hidden PR for those as well. So getting into the threat model. First of all, we are using IP. We talked about this. We get all the good stuff: sniffing, spoofing, replay attacks, and the rest of the family that I'm pretty much sure that you know what I'm talking about. The second thing is that there is no separation of network. Signaling and media share the same network. With the regular PSTN, today, your signaling and your media stream is taking different paths. They have their own different networks. They're going on two different paths. With voice over IP, this is the same network. This means that we can send signaling, we can see the media, we can have lots of fun. And of course, looking at the nature of speech, we need to understand that there are major issues with the nature of speech, such as delay and latency that we cannot have. Jitter, which is delay variation, which is very hard to fix if the delay varies. Packet loss, you lost part of the speech. Speech coding techniques, what the speech coding techniques that you're using. If you're using a good codec that gives you slightly higher or slightly bigger samples, you're using more bandwidth. If you're using a less quality codec, your packets might be smaller, but the quality of voice might degrade. Of course, network availability. You want to take the handset off the hook and you want to hear the dial tone, you want to make the call, and you want to get there. And of course, you need to manage access and priority. We talked about the voice protocols themselves, supporting protocols, the voice over IP infrastructure as well. I'm going to show some examples about phones and servers which were vulnerable to some issues in the past, or some are still in the present. The supporting infrastructure, it's all IP stuff. So you get the same routers, same switches. It's all one big playground. The architectures themselves contribute highly to the amount of risk. We haven't even said it or even didn't touch physical security, and of course the other technologies we're using. So you see this huge amount of stuff that we can have or we can target that will affect our security of the voice over IP network. With voice over IP, we want to maintain integrity, confidentiality, authentication, and non-repudiation. These are all good big words that we are always use, but they are mainly important when we place a call. We don't want anybody to do call tracking on our calls. We don't want anybody to do call hijacking. We don't wish anybody to replay what we said to one another or do eavesdropping to all of our conversation. And of course, there are other fun stuff like active modifications where one can add himself to the signaling routing or even add himself to the voice sample routing, and he will be able to see, hear, and do everything. And of course, denial of service, which is always the last one to being mentioned. One of the core issues with voice over IP and problems with security is the placement of intelligence. With the regular PSTN today, your intelligence or your phone's intelligence is basically stored in the switch. Your phone is a dumb terminal which nearly doesn't know how to do anything. Your switch or your classified switch in your neighborhood is the one that actually do all the intelligent stuff. But this is going to change, especially a network that utilizes session initiation protocol. Instead of having a dumb phone that does not know to do anything, and the control is at the switch, which means that the end user is not able to use a lot of stuff. He needs to go to the switch level in order to circumvent the PSTN. Here we have a phone at our house or on our desk at our office, which is a very intelligent device. The phone itself can send the signaling. The phone itself is responsible for setting up the calls and doing everything. This gives someone a very powerful way in order to circumvent issues. You don't need to go or break in to switches or physically do that like other freakers did in the past. What you need to do is just unplug your IP phone, put the computer in, and you're on. This thing opened up a wider window for problems and opportunities to anybody who wants to abuse the technology. And of course, not all the clients are born equal, so we expect that this will be a major issue. Authentication is another caveat. One of the IBM executive quote from the early days of PCs said that our goal is to make the computer as easy to use as the phone. Now, if you're telling me that when someone that is using an IP phone will have a heart attack, they will want to use 911 or 911 services in order to call in an ambulance, and he will need to authenticate, and instead of hearing the 911 emergency response, we'll hear, please authenticate before you place a call. I don't think that it's good. So that's another major issue. We need to understand that the user and the phone is something that we should not, well, let me rephrase it. We shouldn't let the user authenticate to the phone. What we need to have is the phone authenticate to the different networking devices and the network itself in order to have better security. That's another issue, main issue here. Some of the protocols require one to re-authenticate at some predetermined intervals. If I need to authenticate each time through my phone interface, each 5 minutes, 10 minutes, an hour, that will make my experience with the phone less and less nicer, and probably I will not wish to use that. The devices themselves pose risk. The phones themselves, I'll give example at the end of this part. Servers themselves are at risk. We can target them directly. We can try to get remote access to these servers. We want to get to the management interfaces. Maybe we want to use authentication issues and get unauthorized access. Maybe we want to manipulate the settings or perform call tracking, and etc. And of course, physical access, which is the crown jewel of all of those problems. We can do hard resets, which is basically using a button on the phone and resetting the button to the manufacturer's defaults, which usually will give us a default access to the phone, which the root password to the phone on a managed HTTP server will be blank or something else. We can also use a soft reset, which will do the same. Sometimes the hard reset will not reset the password, so you need to go and do a soft reset to the phone. That's another major problem. Let's say that your kid is playing with your IP phone at home, and he just hitting some buttons and everything, and he resets your phone. What happens there? Where are your configuration files? How can you reload them? How your phone learns about the network? That are major issues. So basically, if you have a physical access to the phone, you can manipulate everything. And the best thing is to have a remote access to the phone where you can play with the settings of the phone. I'll show you an example that by remotely authenticating into a phone as an administrator, you can subvert all calls from the phone, put it on a DND, and the users will not have any clue about what you've done. So the calls will go through, they'll hit the IP phone. The phone is on DND. Oops, send it to my phone, and here I am answering your calls instead of the person that you wanted to call. There are some other issues like uploading firmware, adding and changing functionality, or adding a permanent backdoor, which is kind of cool because you can play some tricks on the phone. You can remotely sometimes give priority to processes. You can do a lot of stuff with it. If we are having physical access to the network, then that's it, basically. We can place free phone calls, we can eavesdrop, we can bypass filtering, quality of service, and such of other things. And basically, you get the picture of what we can do. Some companies that manufacture IP telephony or equipment for IP telephony tells you that you don't need to have double infrastructure. And actually, with IP telephony, what we want to do is use our Outlook, go to our contact list, hit the number, and let the phone do this for us, right? Let the phone ring, place the call, and we'll pick up when the other person will pick up the handset. Now, sometimes it's nice to have this, but we need to understand that if we want to put the tag of critical infrastructure on a shared infrastructure, data and voice, on a same local network, that would be quite hard. Even if we're putting VLANs and separating those networks, or technically separating those networks, if we're going to knock off the switches from the data portion of our network or from the data VLANs, we're going to knock off the voice network as well. They're using the same switch. It's not like they're using something else. If you wish to separate those networks completely, then first of all, it will cost us dearly, and afterward, it might be a challenge to introduce all of those nifty applications and tricks that will work with our IP phones. So in this case, putting the tag of critical infrastructure, which was emphasized after 9/11, on your IP phones or on your voice over IP infrastructure internally in a corporate, it's a big problem. And of course, the most amazing thing and funny thing that if you don't have electricity, then you don't have service, which is kind of cool because what the first thing that we're doing when our electricity is gone and we went to the closet and saw that everything is fine, it's the power plant problem or whatever, and we want to have our electricity back. We call those guys and say, hey, where is my electricity? But if you're using IP phones, if you don't have electricity, you can't call no one. And unless you have a mobile phone or unless you have other means, you can't call anybody and you cannot place anything. That's very bad. This means that if an intruder wants to get into your house and your house is using IP phones and it shuts down the power supply to your house, that's it. If you don't have any mobile phones, I guess you get a picture. This actually violates the E911 regulations, which nobody actually likes to tell you. It's actually some kind of carrier grade availability master issue, and of course, problem with the corporate scenario as well. Cost of redundancy. Nobody's going to put UPSs to all switches and routers along their infrastructure. Maybe in a corporate you can do something, but in a carrier network it's kind of problematic. So I guess for availability you got the picture. Physical security. Last mile is our main concern. Last mile is usually being defined as from your phone at home to the switch. Now, if we get access to the physical wire, it's all downhill from here. Basically, we get access to the wire, we won. The battle is lost, or whatever you want to say, or from different perspectives. If you are going to have equipment placed all over buildings and neighborhoods and stuff like that, there is a chance that some local dudes will come to your equipment and steal it because it's a nice decoration for their salons or whatever. And of course, if some other punks want to do some harm, they're going to cut the cord. Now, if you're cutting the cord of a Ethernet cable, it's a bit more distracting or a bit more problematic than just cutting the cords of the core telephony infrastructure. I don't need to tell you why. So if we look at the example, some manufacturer has an IP phone which has two Ethernet jacks. It's basically for placing or to hook up your PC to the IP phone and provide some simple packet shaping mechanism. Basically, your voice calls and your signaling and voice data will get different quality of service than your computer's data. It's a nice packet shaping ability. But guess what? What if I want to be smarter? So I'm going to take the Ethernet jack that is hooked up to my phone, put it in a hub, take another cord, connect it to my phone, and connect my computer to that hub. Then everything is cool. Because what I'm doing here is that I'm sniffing a while, see what is the quality of service value that is being used, assign it to my computer. If I'm using Windows, that's even easier. All my packets will be flagged with the same quality of service, and here I go. I am on the voice VLAN. And over the voice VLAN, all the party starts, because then I can directly hit all the infrastructure and I can hit all the phones. So if you were telling me that this is the way to secure your infrastructure by using this mechanism, well, it's not. Eavesdropping can be easily achieved if we put ourselves between the phones and between the switches or the hubs, or even between two switches. That depends on the technology that is being used between the switches, and of course regular Ethernet between PCs, IP phones, and the hub or switch. Most interesting thing to put ourselves between a phone and between a switch is our ability to make free phone calls without the knowledge of the subscriber. With regular PSTN today, if we're hooking up between the phone and the switch, and if we're placing a call, what will happen is that if you take your handset off, you'll hear me speaking. With voice over IP, I can make sure that you will not hear anything. And because your IP phone is basically an IP device, it will not take whatever is not belong to him. And I can make sure that that will happen. So I can place free phone calls on your same infrastructure. I'll never know about this. I can even do some tricks that will prevent me from being detected by fraud mechanisms quite easily. One example with access technology, broadband wireless access networks sometimes use LMDS, which is local multi-point distributed service. And if we want to use encryption between base station to residential transceivers, it will cripple the connection so badly so that the LMDS equipment manufacturers are going to tell you not to use it. So basically, if I have the following scenario, if I have a base station and the home transceivers here, for example, whatever will go on the radio will be unencrypted. There are some sniffers, I think by network associates. You just hook them up, you go to the frequency, and here you go. You get all the phone calls of everybody that uses this technology. This is bad. So you don't even need to hack anything. You just go, put your antenna on, get on the frequency, and it's a piece of cake. It's a major problem. Some examples of the past with servers and phones. Cisco Call Manager was affected by the Nimda worm. Interesting, since Call Manager was installed on a Windows 2000 server with IIS on default install. Very bad. There are some organizations which their their mail servers didn't got hit, but since they don't have an antivirus for their Call Manager, guess why? It was hit, and all their voice over IP networks were crippled. And the most interesting example for me is the Aztec advisory, which I've written along with Josh Anderson, which is multiple vulnerabilities with Ping Express SIP phones, which was released on July 12th. Basically, we on the phone, we did whatever we wanted to that phone. We had remote access, remote administrative access. We manipulated all the signaling. We put the phone on a DND and redirected everything to someplace else. There was no icon to alert the user of the phone that the phone is on DND. We had multiple denial services, remote telnet access, local physical administrative access, you name it. We own the phone. From each angle, you did whatever to it. We also by using those vulnerabilities that we have found, we make that phone basically non-fit to be a critical infrastructure piece. This is a phone which actually is regarded as the leading edge for SIP-based phones. Um, I think that the major issues with this particular phone even has not been dealt with yet. So if you have this phone, you're vulnerable to a lot of issues. The company that manufactures this phone, Pingtel, didn't notify its users that this problem exists, although we provided them with 6-page advisory and they replied to our advisory. But if you don't read BugTrack, you don't know that your phone is vulnerable, which is quite a shame because we provided them with all the information needed and with all the time needed to fix these issues, and this was actually a correlated release of information. So this is with this. Also, one of the coolest things that we found is that we were able to telnet to the phone, and the phone is using VxWorks operating system. We were able to give different priorities to different processes on the phone. So this was cool as well. We were able to do call tracking on whatever you want. We were able, one of the coolest things here, that you can actually place calls using the phone interface. So for me to call my other consultant when he didn't want to call me, I just logged into his web interface and called myself. So he was annoyed by the noise the phone made and had to pick up his handset. So as you can see, I can do whatever with this phone. I can control everything and remotely, and it's bad. The DND issue was fixed in a way that they are now put some kind of an icon on the interface. There are multiple issues which all you can read them from our websites, from AdStake's website. You should be able to get the full advisory from there. Other issues such as regulation and fraud, well, it's quite obvious. IETF is ignoring the need for governments for hooking up wiretapping. That's not a wise thing to do, because if you want to put infrastructure like this in countries like the US, the UK, Israel, Germany, if you're not able to hook up wiretapping devices to this infrastructure, you will not deploy this thing. The government will not give you a license. So saying, all right, we don't care about this issue, will not get you anywhere. The next topic that we'll go through will be SIP, but if you have any question up to this point, if someone wants to ask something. No, okay. Yeah, sure. There is a way for the phone to work with a switch and to get his power from a switch, but it's like, it's not a carrier grade switch. It's like those Cisco switches that are able to power phones and able to power other devices. There is actually some kind of regulation to do that. But if this switch goes down, then again, you have the same problem. Some people, I don't know if they tested this on really lengthy connections. Sometimes they have to put an intermediate switch in your own building, and that switch will be connected to the class 5 switch or something like that. Maybe there are some hops in the way between you and the class 5 switch, and by knocking off one switch along the way, you knocked off your power to the phone, and your phone is useless. Yeah. Sorry? E911 says that, if I'm not mistaken, says that when you place a call, you need to be located, and when you place a call, you must be able to place a call to emergency services from your infrastructure. I'm not saying that if someone will not cut the cord on the regular PSTN phones today, you will not be able to place a call, but the way that the phones work today on the regular PSTN are quite different than it's been working on IP phones. The power consumption is totally different. No. I think it's quite different. I think Europe is different too from the U.S. Yeah. Yes. I don't have the numbers. On Usually there will be more phones deployed in North America corporates than in any other place. The phone that I've mentioned here, the Pinktail Espresso phone, is on the psych list. If you know what the psych list is, it's basically, this means that the federal government can buy those phones without any problem. I guess this raises the bar and the question on how these devices are being evaluated for their security for the federal government, which I think some people need to think about. Does this answer your question? Yeah, well, I guess it's something that we need to go and ask companies like Cisco, Pinktail, and other voice over IP manufacturers like Nortel and stuff like that. I don't think that they will provide the numbers. Yes. You don't need to use you mean authentication to the phone itself? That depends on the architecture that you're using. If you're using, for example, MSN messengers and you're using that in order to place calls over the internet, then you must have authentication, and the authentication actually is being encrypted in some way. If you're using your own phone at home and in that deployment scenario, sometimes I was talking more of the generic way the protocols are being built rather than the devices in that issue. Sometimes the protocols themselves will say, or the RFC itself will say, we need to authenticate in this way. But the RFC does not make the difference between a user and a device. This means that your phone and you are basically the same entity. It will be wiser for those RFC to state exactly what they want to have. I'm not saying that doing authentication from device to device is best, because if you crack the device, you get the authentication information, and from there on, it's downhill again. Does that answer your question? Okay. What we're going to do next is look at some characteristics of the session initiation protocol, which is basically the Cloud Contender as the #1 signaling protocol which is used on all voice over IP networks. There will be some kind of slides next that will outline the way SIP works, which are essential to understand where the security problems and when the fun starts. If you have any questions with the slides, or you want to ask something about the functionality, just raise your hand, I'll answer the question. Basically, SIP was developed under the IETF, started in 1995, first standard RFC 2543, 1999, and just last month, the new SIP RFC 3261 was published by the IETF. Its definition, which is application layer control protocol that can establish, modify, terminate multimedia sessions such as internet telephony calls. It can also invite participants to already existing sessions. Media can be added and removed to existing sessions, and all the other nice things that we want to have with a good signaling protocol. Interesting. SIP supports basically 5 facets of establishing and terminating multimedia communication. User location, user availability, user capabilities, which basically determination of the media and media parameters to be used, session setup, and of course session management, which is kind of cool thing because you can transfer and termination of session, modify session parameters, and invoking special services. This example actually shows the classical or the basic functionality of SIP, locating an end user, signaling the desired communication, setting up the session, and tearing down. In our example here, Alice's PC here uses SIP application on the PC. It's actually being called a soft phone. And Bob here is using a regular voice over IP phone. These two entities are called SIP proxies that are being used by both Alice and Bob in order to send the SIP signaling. Now, SIP is much like HTTP, and some characteristics are even taken from SMTP. Not saying that it's a good thing, but at least it will be easier to understand to some people. Alice calls Bob using his SIP identity, which is called SIP URI. In our case, it's this thing. You can see that this is basically a regular URI, that the SIP name and two dots here were added to the URI to have what they call a SIP URI. We are actually sending this to Bob's domain, which is biloxi.com, and Alice uses her own SIP URI to identify herself, which is under the atlanta.com domain. If we look at the initial invite that we're sending, we can see that we have a method name which starts our packet here. We can see that an interesting header called via is being added to the operation here. Via basically identified the node on which Alice is using her PC. In our case, it's pc33.atlanta.com. Each SIP server or SIP entity along the path from Alice to Bob will add its own via header. In this way, when we arrive to Bob, when the packet arrives to Bob, Bob has all the information it needs in order to route back to Alice on the same route the initial invite was routed through. Another interesting thing is the call ID, which contains a globally unique identifier for this call. It's very important, and a classical sequence number. A contact name contains a direct route to Alice. In our case, pc33.atlanta.com is the direct connection to Alice's PC. The details of the session, the way we want to use the media, the codec that we want to use, the sampling rate, and each and every other information is being put on the SIP body. The SIP body is a MIME type, which is being described by another protocol called SDP, which is RFC 2327. If we look at the overview of the operation, at first Alice wants to call Bob, and she does not know the location of Bob. Therefore, she sends an invite, her soft phone sends an invite to her proxy server, which is this Atlanta.com SIP proxy server. It's not the same proxy server you know from. It's a SIP proxy server, which is usage is to route or to send signaling on behalf of its users. The proxy server gets the invite, and it will generate a 100 trying message back to Alice. The 100 trying message actually tells Alice that the message was received by the proxy server, and the proxy server is now trying to read the message and to act upon it. The next thing to do is for the proxy server to determine where he needs to forward the initial invite Alice sent. Now, the proxy server looks at the DNS and understands that he needs to forward this invite to the biloxi.com proxy server. Just before forwarding the invite request to biloxi.com proxy server, he will add his own via header to this invite. When the proxy server will receive this invite, again, it will generate a 100 trying response message back to Atlanta.com proxy server saying, yeah, I got this invite, thank you, I'm processing it. For biloxi.com proxy server to locate Bob's IP and to understand if Bob does belong to biloxi.com, SIP proxy server's area of the area in which it is in charge of, he needs to call a service called location service, which basically holds Bob's SIP identity, and against that SIP's Bob's current location. This means that Bob's IP will be there, or Bob's exact DNS location and things like that. Basically, what we'll do, the Biloxi.com SIP proxy server will go probe the location server for the location of Bob and see if it has an entry for Bob. If so, it will get the information where Bob is located to and will forward the request to Bob. When the SIP phone of Bob will receive the invite message, again it will send a 100 trying response code back to the proxy server. Then he did receive it. The phone will ring, and then it will send a 100 ringing message back to the proxy server of Biloxi. That ringing actually will be routed back to Alice, and then Alice's soft phone will start to ring as well. If Bob decides to pick up the handset and answer the call, he will send a 200. The phone will send a 200 OK back to Alice saying the call is set up. With that 200 OK, there are already in the media description of the type of session that Bob is willing to establish with Alice. The information that was sent on the initial invite from Alice contained the parameters that Alice can deal with. And the 200 OK send back the parameters that Bob want to use and can use. If we're looking at the invite that actually reached Bob, we can see that we have multiple VIA headers. Those VIA headers were inserted by the different entities of SIP along the way. If Bob is not willing to take the call, or if Bob is busy, his phone will issue a 486 response, which will say, "I don't want to take this call." Now, the proxy server has a choice to redirect the call to a different place, either to a voice messenger, either to another place, whatever. The proxy server is a very, very smart entity that can control whatever aspect of the call. For the 200 OK, Alice's phone will send an acknowledgement, and after the acknowledgement will be received by Bob, the real-time transport protocol media stream will be opened up peer-to-peer between Bob's SIP phone and to Alice's phone. From this example, you can see that the acknowledgement is also being sent peer-to-peer. This means that those two proxy servers are no longer on the path for those messages. This means that by the time the 200 OK reaches Alice's PC, Alice knows exactly where Bob is, and she can directly connect to Bob. During that particular session, we can send a re-invite that will change the parameters of the media that was established between Bob and Alice. A re-invite is a very powerful way in order to circumvent any SIP-based signaling. Some parameters of the re-invite should be the same as the original invite, but it can also hold some information about different routing path, different participants, different codec to use, and such and such. At the end of the call, we can see that a buy request is being sent by Bob's phones. Basically, Bob puts the handset down, sends a buy request back to Alice, and for that buy request, we get an OK, and this is a tear down. Some of the proxies are also able to force some routing if they introduce a field called record route. If they introduce a record route field inside the invite, all the subsequent messages will go to that particular proxy server as well. In this example, the Biloxi.com proxy server inserted a record route to the invite message he forwarded to Bob. That information was also sent back to Alice when Alice got the 200 OK message. Therefore, when Alice replies to the 200 OK message, it sends it to the biloxi.com proxy server, and whenever other messages of SIP are being sent between the two parties, those signaling will go through the proxy server. Sometimes it's a very good thing to do if you want to maintain a billing record. But if you have a malicious client, then you can say, oh, you know what, I don't want to relate to record route records, and I just drop them. And if you write your own stack, or if you write your own application, you don't care about where the thing will go through. So basically you can say, oh, I got the record route, it's nice to know, but I'll drop it and I'll open up a direct communication channel between me and the other participant. What if you are being charged by your phone company, then what is being done here is just they will see an open session that is not being teared down forever. Another very interesting way of letting others know where you are is the operation of registration. In our case, Bob's phone, when it boots up, sends a register request to the registration server, which can authenticate Bob or just get the register message, which says Bob's SIP URI is this IP now. This information is being sent to a database, which is our SIP location service, and when a proxy server wishes to extract that information, it will query that SIP location service, get the records 1 or more or 0 or more, and know if Bob is actually reachable or not. Another interesting thing is the cancel request. If we have a pending invite, we can send a cancel request, or the Alice PC can send a cancel request to Bob, canceling the call. Okay, the cancel will be applicable or being able to be used only before 200 OK is received. And if it's received on Bob's end correctly, we'll get a request timeout, a request terminated, sorry. If a 200 OK was already being sent, we'll have to tear it down with the buy request. So, enough of the boring stuff. There are several methods that I've described to you: invite, ACK, buy, cancel options, and register. There are several response codes that we'll get to them in a minute. And here's the global way of doing stuff with SIP. We first boot up, register, store the information in the location service. We're being called by Alice. Her call is being forwarded, or the invite is being forwarded to Bob. After the SIP proxy has queried the location service, the ringing is being forwarded, the OK is being forwarded, acknowledgement, and there is the media transport, which is open up. Their RTP stream is open up, and it's peer-to-peer. Then here we can see an example of tearing down the connection, sending a buy request to Bob, and OK, and the session is teared down. If we have a redirect server, everything is the same, but when the SIP proxy of Atlanta.com tries to go and understand where it needs to forward the invite to, it might send it to a redirect server. A redirect server will only inform the proxy server of where next he needs to send the information to. So here we have a redirect message back to the SIP proxy with the information that it needs to forward it to the biloxi.com SIP proxy. And of course the other parts are exactly the same. Now, SIP also supports mobility, which means that we can register on a couple of different places. A SIP entity or a SIP URI can be associated with one or more IPs. This means that when we try to reach Bob, his phone, his work phone, for example, might be switched off, or his phone might be having an information where to send the invite to. For example, if he's at home now, or he's using his mobile phone, or other things like this, there is a special response code called a redirect with the information where to send or where to forward the invite to. In our case, this information is being sent back to the Atlanta SIP proxy, which redirect the invite to the appropriate place in which Bob is currently in. This is all fine and well. This is pretty much the way how SIP works, and it was essential for you to understand the security stuff that we're going to speak about now. First, I want to say that with RFC 2543, UDP was the transport protocol for SIP. Then, for the new RFC, the IETF actually demanded that security extensions will be added to SIP. And because you can use only IPsec in order to secure UDP, they had to choose something else, and they had to go for TCP. This is after years and years that people smear TCP of being not applicable and not good for sending signaling stuff because of the different retransmission mechanisms and the way TCP ensures delivery. So Dorothy had to buckle up because Canada's gone bye-bye. Those security stuff that they have added into SIP are not good enough, and they still have a lot of information which is wrong, or it is bad. I'm not going to look at the security mechanism themselves, but instead of that, I'm going to show you what you're not going to get if you're not using any security mechanism. Most of them are dependent on the usage of TLS or even IPsec. Well, I don't need to tell you that IPsec is a nice thing, but sometimes it doesn't work if you want to, and especially across networks and with different networks of other participants and with different equipments and stuff like that. It's very nice, but sometimes there are problems. But I'll try to show you where you can defend yourself as well. So we have quite a lengthy list of denial of services, call hijacking, man-in-the-middle attacks, cover channels enumeration, and things like that. And I'll start with how we can sabotage the setup of a call. So Alice is sending an invite to Bob. All the usual stuff, the invite request is being forwarded and the ringing message is being sent, and someone malicious inside your organization, as you can see here, Carol, will just send you a cancel request with all the information that it needs in order to match with the original invite. What your UA will do in this case, it will cancel the request, and whenever something else will be forwarded from Alice to Bob, it's already gone. There is no transaction on the UA. There is no way of setting up the call. You can also do this from another side, if you are on Alice's side. If you are able to watch what Alice is trying to do, and if you are seeing that Alice is trying to communicate with the world, and you see the 180 ringing coming, what you have to do is just cancel whatever Alice is sending out. Cancel whatever Alice is sending out, and here you go. You make a denial of service on Alice. On the other case, you did a denial of service on Bob, but he was the target. So any target Alice is trying to talk to, she will fail. A buy request is a termination of a call, which you can also use in a quite similar manner. We're setting up the session again. All the parameters are correct. We open up the media stream, and then Carol actually sends the C proxy a buy to be routed as either Bob or can be routed to Alice. Now, as soon as the 200 cable will be sent from Bob's SIP phone to Alice's SIP phone, Carol will send a buy request to either Bob or Alice or both and basically tear down the connection. So here we're sending down a buy request to Alice. That's it. Alice sends a 200 OK, and what subsequently will be sent from Bob to Alice will be ignored because the transaction is not there anymore. If we will get actually a response code saying that the 481 call transaction does not exist, and basically that's it. We can do the same trick, and we can send the buy request to Bob. It's the same thing. If subsequently requests will come up from Alice to Bob, the same thing will happen. We can do a nice trick that will make fraud systems really blind to this kind of attack. We will send buy from Carol to each participant, with the same sequence number. What this will ensure is the 200 OKs that will fly by will have the same sequence number, and it will look like legit to whoever looks at matching the buy request to the 200 OKs that follow up afterwards. We can also use response code into introducing either denial of service or call hijacking. If we're using 4XX responses, these are basically a definite failure responses, which we send back to someone if we couldn't process or do something because some kind of piece of information was missing from the request. The client should not retry the same request without any kind of modification that it needs to add. This means that if we send an invite and we had to be authenticated, we will get a 401 or a 407, which tells us that an authentication information needs to be sent to us. 5X and 6X responses are total failure responses that should result in the stop of the initiation process. So if we're looking at call hijack using those messages, the way to do this is quite simple. We see that Alice started the invite process, wants to have a conversation with Bob. All the other subsequent messages are being exchanged. The information is, one second, I lost track here. The information is being, okay, sorry. As we can see here, Bob sends his register information to the register. The register stores the location, the information at the location service, and what Carol is doing is associating Bob's URI with the attacker's machine. It goes to the register and actually tells him the SIP URI for Bob is this and that address. And that address is Carol's address. So whenever Alice will try to initiate a connection with Bob, and whenever the proxy, SIP proxy will try to get the information where Bob is located, instead of actually going to Bob's IP phone, since the location service now shows that the IP for the SIP URI for Bob is the IP of the phone for Carol, that reply will contain that information, and then the invite will be forwarded to Carol instead of to Bob. Questions about this? You can add authentication. Sometimes there is no authentication. If there is no authentication, you will be able to inject whatever you want to that. The authentication that is being supported is regular HTTP authentication, digest, and also you are able to use TLS between the UA and register, but nobody is using that, and it's not being implemented by any manufacturer yet. Sorry? I don't hear you. Certificate in the phone. You get to another interesting way of how you handle certificates and where you want to handle them, and what kind of power those phones has, and the amount of megabytes that they have to store the information. These phones has very, very small power or in very, very small storage area. And there's also a very, very big and hard questions about how they're gonna use that certificates, and how they're gonna use a certificate server in the way that will authenticate themselves to the different servers and such and such. There will be a delay, and someone will have to pay for that delay. And you know who will pay that? The user, you. So it's nice in a top secret military network. It will work nicely. You know, people will say, yeah, we'll hear the scrambles noises, and after 5 seconds, you know, the session will be set up and some kind of a delay. But if you want to have this on a carrier class network, forget it. It never work. This is why encryption is really bad for this type of stuff. If we're querying the SIP register, we can get a list of addresses of particular SIP URI. We can get a list of addresses associated with that URI. But if there are more addresses when we register than it should be, your IP phone will not show it to you. So if someone is manipulated with your records and you still register and you get all of those records back, you still will not be able to look at them because it's not being displayed to you. You shouldn't look at them. So you're not able to understand that someone is trying to play with you here. We can use some tricks on the registration records. We can register with a lower priority and perform denial of service on the IP phone. And when the proxy server will try to forward it to the IP phone, it will fail. It will take the next entry in the registration information required to connect to. It's us. There are some issues with authentication. Well, mainly this is the expires issues with the registration records. This means that there should be some kind of a device authentication rather than a user authentication, and if that authentication information is being held on the IP phone itself, and you have the full access, like we had the full access to the Pington Express files themselves, we were able to extract whatever files we wanted and take whatever files we wished. So we were able to upload and download stuff. So for example, we were able to load up ringtone, which is 0 and without any tone. So even if the phone rang, you didn't understand that it rang and you would not answer. Some simple stuff like this. Sometimes this information will be stored along your configuration file at the phone, like another example with Pington Expressa. So you could just extract that information. You have remote access and just get that information, and you can register with that information. Basically, this is your ticket to heaven. So you use that information and you use whatever you want on the SIP network. Call hijack can be done with different response codes as well, like 301 move permanently response code. Invite is being sent by Alice, being sent to the proxy server, and when Carol sees that, he sends a 301 move permanently response code, which basically carries the new or the fake IP address for Carol as the place in which Bob is being now, and of course Bob is not where Carol is, and Carol just performs a call hijacking. There is a move permanently response code, which is fairly similar. It's just sometimes it's that's basically the second part of this slide. Some other interesting stuff, the 302 move temporary response code, where we say, oh, temporarily the phone is down, we can use another venue. This is another issue. If we're going to send re-invites to the session, what we can do is either hijacking the signaling path, either we can deny signaling from any side by introducing ourselves on the path or putting ourselves as a critical path to go through when Alice sends information to Bob and Bob sends information to Alice. This means that we'll get the signaling information and we will decide if we want to forward them in the way that we want to forward them. And if those parties want to use kind of interesting stuff, we'll be able to review it. Man-in-the-middle attacks, we can do man-in-the-middle attacks against all the different servers and the UAs. I'll go to the more interesting one. Whoops. I called it the Who's Your Daddy attack. Basically, Alice sending the invite to Atlanta.com SIP server, and immediately what Carol's proxy technically doing is send a very interesting response code who is 305. The 305 is actually a very nice thing because the proxy is advising you to use another proxy. So here you go, I'm sending you that, I want to help you. So use this proxy. So you build your own proxy software on Alice's fake proxy and you get everything. Now this can evolve even to a bigger and more effective issue, since what I can do here is I can say, you know what, Alice, I need your authentication. 1 second. I need your authentication. So Alice will send the authentication in order for me to forward the packets, and here I go. I get Alice's authentication information as well, and then I don't need Alice anymore. I can place whatever calls I want, saying that here are my credentials, and go out and use whatever I want. Yes? Yeah, you need to spoof the source IP address. Because if you're not spoofing your source IP address, the packet you are sending will not be accepted by the TCP/IP stack. Yes. I didn't hear. Can you say it louder? It's a good question. The gentleman at the back asked if the SIP identifiers can be predicted. In the past, well, basically you have to have four different parameters. You have to have the call ID, the correct sequence, which is easy to predict, the to and from fields. You also have to have some kind of tags on your to and from, but if you're on the wire, it's fairly easily. There is one remote attack that you can perform on registration, which does not require you to understand the call ID, and I can't really talk about this because it didn't really be published yet, but there is an attack on some phone that, because of its uses, quite clear to understand call IDs when it's registering, you're able to hijack whatever registration it did. So these are valid problems. Did it answer your question? Let's go a bit faster here because we have 5 minutes more. Yeah, I see the zero, but I'll take 5 minutes more and I'll finish this up. Signaling goes one way, media goes another way. This means that we don't have any synchronization between the signaling and the media. If I want to change parameters on the media path, I can do that. The signaling will not understand what I'm doing. I can change media parameters through the signaling, but I can do that directly if I sniff the media path information. That is very bad. This means that I can change actually some parameters on the media without the knowledge of the signaling, such as the codec. I can use a better codec, which utilizes more space for the packets it sends, and if it's on a very bad link, what it will do, it will congest the link and we'll start to losing packets. If you remember the voice quality issues, here I do a simple denial of service attack. Or I can do otherwise. I can use a very bad codec and just degrade the voice quality that we have. We can enumerate some of those servers. We can use, for example, if we get 481 for our cancel request, we understand that our late transaction does not exist, or maybe we'll try to use another call ID, maybe we'll change our sequence. This will allow us to brute force those abilities. There's the options method, which is basically tells us what exactly that server is able to perform. We'll get that information, will help us to query it. Max forwards, for example, if everything is encrypted, for example, and I want to understand which are all of those SIP entities along the path from me to my friend, I can play with max forwards like a TTL, which is basically the same issue, the same way max forwards works, and I will be able to enumerate all those hosts along the way to the target. Now, all the firewalls, if they will be present along the way, will not be able to look at that max forwards if the information will be encrypted. Cover channels. If I am having a fake SIP header, it will go through because we have future header support. So if the SIP proxy does not understand what you're talking about, it will let it through. A perfect cover channel. Call tracking. When I get the invite message, I get all the information that I need. I get the where are you calling, when you're calling. Basically, it's like capturing DTMFs. And if you're actually using that in order to send your or do online purchasing, very, very bad. Or to pay your phones through your bill through the phone, very bad. One of the last things that I'm going to mention is that the IETF does not regard clients to be malicious, which is very bad for their perception. They think that clients will be perfect because it's their organization and the way that their organization is being using those phones. Well, like in each society, there are a percentage of people who are malicious. I don't need to explain that. Even if all the paths might be encrypted and everything, when the message hits Bob, and if Bob is a good friend of mine and I want to try to get to Bob directly, if the networking infrastructure is not configured good and will allow a directly connected link for me to Bob, not using RTP but using other protocols, what I can do, I can call Bob and say, Bob, what is your IP? Or I even want to try to bypass some elements, I can call Bob and say, listen, when your phone rings, just hook up your computer in the way I told you and send me the dump. And with that dump, I'll have all the information I need from the via headers for all of those servers that it passed along the way. So I'm going to say, oh, maybe I'll now start to send it to those servers directly, or send my information directly to Bob, and try to eliminate the way that my company or the telecom company do billing. There are way more issues like predictive values. Thank you for reminding me to talk about that. Firewalls and that, it's not going good together. Bypassing C proxies or bypassing billings. There are a lot of other issues here that I didn't relate to. There are several mechanisms within SIP that are basically futile. They're not working. They're not being implemented. It will be really interesting to see if they will be able to do that without the penalty of latency. If you put encryption on your real-time transport protocols, if you put encryption on top of the problematic way of sending data inside packets or voice sample inside packets, you introduce more latency, and we're talking about 200 milliseconds to 250 milliseconds. You put more than that, you kill your voice quality. One interesting thing, last thing with RTP, which is the last thing to mention here. With RTP, there are two crucial parameters, the sequence and the timestamp. What one can do, if two parties are calling or talking to each other, if I'm in the middle, and if I'm using a higher sequence and a higher timestamp, my packets will hit whoever and will be heard on that part. So if I want to send information to whoever party is here, all I need to do is take the sequence and the timestamp higher to the future, and whatever you send will be ignored. So I can just play whatever I want to each other parties, and you will never be able to contact your party ever again. This is practically it. It's a lot of information to be talked in 1 hour and 20 minutes. But if you have any question, please ask. If you want to ask questions in the future, just email me. Yes, one question here. SIP is usually the protocol that more and more companies will use now in order to do signaling. The other protocols are like H323, that's mainly it. H323 and SIP are the main two protocols that we have.